Today, what I'd like to do is explain the support for dynamic datums in Trimble software. Semi-dynamic datums are datums that contain a 14-parameter transformation from the ITRF to a national datum, and they also crucially contain a deformation model, which allows us to correct from the epoch of measurement, when the measurements are made, to the national datum, reference epoch. The Trimble software contains 4 different types of deformation models. The first and simplest is an Euler pole, which allows us to measure the motion of the underlying plates, but no tectonic deformation at all. The next model is an average velocity model. In this case, we have a grid which allows us to accurately calculate the velocity of the point which reflects the underlying tectonic motion for areas like the western margin of the U.S. The third type of model contains a velocity grid and an earthquake grid to correct for earthquake motions for areas that are undergoing significant seismic disturbance, and also post-seismic if that's important. The fourth type of model is a total displacement grid, and that contains a grid which gives us the total deformation between the reference epoch and the point in question. And this is for countries that produce models of total motion, which are generally updated yearly, such as Japan. And we can incorporate all of those in Trimble software. This map shows the models that we have currently, and as you can see, they cover the whole world. There's also a lot of white for areas that have no deformation models at present, but we're confident that as these countries adapt models, we'll be able to accommodate those also. To illustrate how these work, consider the CON-US. In this case, we have a velocity model consisting of 5 nested grids. The base grid is a velocity grid which is low resolution, covering all of CON-US. We also have high resolution grids along the tectonically active western margin, and an ultra high resolution grid for the San Andreas Fault. We have 2 earthquake grids in this model also, one for the Sierra Almeja earthquake of 2010, and another one for the Ridgecrest earthquake of 2019. And the Ridgecrest earthquake involves two nested grids, one covering all of Southern California, and a second high-resolution grid which is right over the epicentral region. And we need that because this earthquake broke the surface, and so we have very high spatially spatial motion in this area, and we need a high-resolution grid to model that. In conclusion, Trimble software has been upgraded to support time-dependent datum transformations. It includes a grid-based algorithm that is fairly general, and we're confident will support deformation models anywhere in the world, or any deformation models that are likely to be introduced in the near future. It's also generally consistent with the OSG's proposed standard for deformation models, and once again, I think this gives us confidence that the software will continue to support deformation models as they're introduced in the future.